Hi guys and welcome back to the channel. Unless it's your first time here, which it probably is, let's be honest. What we're going to be doing today is we're going to be looking at taking the derivative of a scalar function multiplied by a vector. Both of them depending on the same parameter. In this case, we're going to be looking at the usual parameter t. So we're going to be taking the time derivative. And starting out, we're going to define our scalar function as f of t. Function takes in a time and spits out a number. And likewise with our vector r, we are going to take in a time and it's going to give us out some vector r, usually a position vector, but it can be anything. And you might come in a situation where you are multiplying this vector by the scalar function itself. You might think to yourself, I want to take the time derivative of this because I can. And you're going to ask yourself, oh, what's this going to give us? Well, it's a fairly simple application of the product rule, where we get f of t multiplied by the time derivative of r plus the time derivative of f multiplied by r itself. And this is it. This is all there is to taking the time derivative of the scalar function multiplied by the vector. So first things first, we are going to define a new vector. We're going to say let vector f be equal to this new vector that comes out from f of t multiplied by r of t. And applying a certain definition of the derivative. And the definition of the derivative that we're going to be looking at would be dr of dt is equal to the limit as a small change in time goes to 0 of a vector at t plus this small change in time minus the vector at its original time all over the small change t. And this is the usual definition of the derivative. But we're going to be applying this to our new vector f in this case. And this is what's going to form the basis of the proof. So now that we've defined what the derivative is and our new vector, we're going to want to combine these two ideas. So if I can find the line, there we go, just got to separate that. So let's start off with taking the derivative of f and just directly applying the definition. So in this case, oops, don't want the blue, get. So we'll have df by dt is going to be equal to the limit as delta t goes to 0 of f at a time t plus delta t just a small change in the time, plus f at its original time t, once again all over delta t. Now, from here, let's substitute in the very definition of f. So getting rid of that, we can say that the limit as delta t goes to 0 of f at time t plus delta t multiplied by r t plus delta t minus f of t r of t. And it's just straight applying the definition. And now this is the part where the trick comes in. We are going to do what all good scientists and mathematicians do when they come up against a proof problem. They add 0, but we're going to add 0 in a slightly different way. We are going to add and subtract f at t plus delta t multiplied by rt. Please excuse my horrible handwriting here. But yeah, this is the main point, and this is the main trick to doing this proof. So, with this in mind, the limit as delta t goes to 0. And adding this in, sorry, I should have specified that this is all over delta t to make any sense. But yeah, so gonna get rid of this. So applying it to the above, we get the limit as delta t goes to 0 of f at t plus delta t r t plus delta t minus f t rt, and now we're going to add 0. So plus f at t plus delta t rt minus f t plus delta t rt. And this is once again all over delta t. Okay, now it looks long and it looks complicated, but we're going to split it up. It's only 4 terms. 1, 2, 3, 4. So, splitting it up, smartly at least, we are going to rewrite this, first of all, as this term and this term. And then finally, we will split the other side into what's left. This term plus this term. And you're going to see why in a second. So, moving it up a little bit, we find that we get the limit at delta t goes to 0. Now let's focus on the purple part here. We are going to have f t plus delta t times r t plus delta t minus f of t plus delta t rt all over delta t. And added to this, we're going to have the other side, the green side. So the limit, once again, of delta t goes to 0 of f t plus delta t r of t minus f of t rt all over delta t. Okay, now having a look at this, you can see that on the left hand side we can take out this common factor here, and what it's going to leave us with, I think you can see, is actually just the definition itself of the derivative, where we had the same derivative up here as we do down here, and that's what's going to be left. And the exact same on the opposite side where the green terms are, but with the green terms we are going to be taking out the r of t itself. Oops, swear there wasn't an earthquake. R of t here, and it's going to leave us with the definition of the derivative of the scalar function. So, going along with our original idea, get the limit as delta t goes to 0, ft plus delta t, and then square brackets r t plus delta t minus r of t. And this is all over delta t. And on the other side, we have the limit delta t goes to 0 of taking r of t out and leaving f t plus delta t minus ft all over delta t. Now, I think it's fairly clear what's going to happen here. We can split each fraction into these parts here in the blue. And taking away this line, it's fairly easy to see that as we take the limit as delta t goes to 0 of the first term here, this ft plus delta t, well, all that's going to give us is f of t. And for the second part, well, we know that the limit as delta t goes to 0 of this is exactly the same as the definition above. And this is going to give us r dot, where r dot is the same as the time derivative of the r vector. And on the other side, r of t doesn't have any delta t components itself, so we can just say this is plus r of t. And finally, this last part is just the definition of the time derivative of the scalar function. And that's going to give us f dot t. And that is our final answer. Now, I know it's been a bit of a slog to get here, but we did. We started off at the very top with our two definitions. We had the definition of f, and we had the definition of the derivative. And from this, we've went all the way down, adding and subtracting 0 of this ft plus delta t rt over delta t. And with clever rearranging, we come to see that the product rule gives out the scalar function times the time derivative of r plus r times the time derivative of the scalar function. Right, well, I hope this has been helpful. And, you know, if you've liked what you've seen, or if it's been helpful in any way, not sure if it would be, but if it is, give it a like, a subscribe maybe, and yeah, I'll see you next time.